Hello everyone, welcome to today's session on OSI TCP UDP models, the fundamental building blocks of networking. My name is Zishan, and over the next 60 minutes, we are going to explore how data travels across networks from the moment you click a link in your browser to when a web page appears on your screen. Whether you're troubleshooting network issues, designing systems, or simply curious about how the internet works, understanding these models is absolutely essential. They provide the framework that every networking professional uses to think about and solve problems. Today's session is structured as a comprehensive 60 minutes guide. We'll cover everything you need to know to understand these critical networking concepts, and by the end, you will have practical knowledge you can apply immediately. Let me walk you through what we will cover today. I have divided this presentation into two main parts, each lasting 30 minutes. In part 1, we'll focus entirely on the OSI model. We'll start with an introduction to what the OSI model is and why it matters. Then we'll dive deep into all 7 layers, explaining what each one does and how they work together. We'll explore how data flows through these layers and see real world application of this knowledge. Part two shifts our focus to TCP and UDP protocols. We'll examine what makes these protocols different, when to use each one, and how they fit into the OSI framework we just learned. We'll compare the OSI model with the TCP IP model that's actually used in practice. Look at practical examples and finish with troubleshooting strategies and best practices. Throughout this presentation, feel free to ask any questions, drop a comment, and you can ask questions. Now, let's begin with understanding what the OSI model actually is. Now, what is OSI model? The OSI model stands for Open System Interconnection, and it was developed by International Organization for Standardization in 1984. Now, you might wonder why we need to learn about something from 1984 when technology changes so rapidly, right? Here's the thing. In the early days of networking, every vendor had their own way of doing things. So IBM had its own approach, DEC had its own approach, right? And so on. It was like having different manufacturers, making a car parts. Let's suppose there's a car parts and different manufacturers are making a different car parts that couldn't work together. The ISO created the OSI model to solve this problem by providing universal framework. Now, think of OSI model has conceptual blueprint for network communication. It takes the incredibly complex process of sending data across networks and break it down into 7 distinct manageable pieces. Each layer has specific responsibilities and protocols. And here's the key point, each layer only needs to know how to talk to the layer directly above and below it. This creates what we call abstraction. The application layer doesn't need to know anything about electrical signals or cable types. It just knows how to hand data to the layer below it. This separation enables interoperability between different network technologies and make troubleshooting much more systematic. The beauty of this layered approach is that it simplifies complex networking concepts, enables troubleshooting, and provides the standardization that makes the modern internet possible. So, here we see all 7 layers of the OSI model. Let me give you a memory aid that networking professionals have used for decades to remember these. All people seem to need data processing. So this is a sentence which you can remember to remember these 7 layers of OSI model. All people seem to need data processing, where A stands for application, P for presentation, S for session layer, T for transport layer, N for network layer, D for data layer, P for physical layer. So all people seem to need data processing. This helps you remember the layers from top to bottom: application, presentation, session, transport, network, data link, and physical layer. Notice how I am presenting these layers from layer 7 down to layer 1. Right? This isn't arbitrary. It reflects how we typically think about networking from users' perspective. You start with an application like browser, and that application uses services provided by each layer below it, all the way down to physical cables and wireless signals. Each layer adds value by providing specific services. When data moves down through these layers from application to physical layer, each layer adds its own header information. Think of it like addressing a package for shipping. The application puts your data in the package. There's a package, data is inserted in the package. The transport layer adds delivery confirmation requirements. The network layer adds routing information and so on. When the data moves up through the layers of receiving end, each layer removes its header and processing the information relevant to its function, then passes the remaining data up to next layer in the receiving end. This is has a sending end. Top to bottom is a send. Top to bottom is through a sending end. Bottom to up is a receiving end. This is the foundation we'll build on as we examine each layer in detail. Remember, both TCP and UDP, which we'll cover in the second half, operate at layer 4, the transport layer here, which is TCP and UDP. We'll talk in the second session about this. Now, let's start at the bottom with layer 1, the physical layer. This is where networking meets the real world, where digital information becomes actual, measurable signals. The physical layer's job is to handle the physical transmission of data. It defines how bits, those ones and zeros, when I talk about bits, it's ones and zeros, that represents all digital information, get converted into electrical signals on copper wire, light pulses on fiber optic cables, or radio waves for wireless communication. Think about what happens when your computer sends a simple 1 1 or 0, the physical layer defines exactly what voltage level represents 1 versus 0, how long each signal lasts, and how to synchronize the timing between sender and a receiver. The physical layer also defines the mechanical and procedural specifications. This includes things like what type of connector to use, how many pins it should have, what each pin does, and even physical layout considerations like whether you are using a star topology where everything connects to a central hub, or bus topology where device connect along a single cable. So examples of physical layer components include the actual cables. What are the actual cables? It could be cat 5e or cat 6 ethernet cables. What we talk about, here, ethernet cables, network interface cards that convert digital data to electrical signals. Then we have hubs that repeat signals and repeaters that amplify signals over long distance. Physical standards include specifications like 10 base T, which defines 10 megabit. 10 base T is nothing but which specifies 10 megabyte 10 megabit Ethernet over twisted pair cables, or a physical specification for Wi-Fi that defines radio frequency and power levels. When troubleshooting network problems, physical layer issues are often the easiest to identify but can be the most frustrating. Things like loose cables, damaged connectors, or signal interface. Moving up to layer 2, the data link layer, we transition from raw electrical signal to organized, structured communication between directly connected devices. The data link layer takes the stream of bits from physical layer and organizes them into frames. From physical bits to organizes them into frames. Think of a frames as envelopes that contains your data along with addressing information and error checking codes. So this layer actually consists of two sublayers. The MAC layer, which we also call it as, what is MAC? The full form of MAC is nothing but media access control, handles physical addressing using MAC address. Every network interface has a unique 48-bit MAC. It would be like something 001B, 44. I'm just writing a random MAC address number. So this is how your MAC address looks like. The MAC sublayer also manages access to the physical medium. For example, in tradition Ethernet, it uses CSMA-CD, which is carrier sense multiple access. We call it as CSMA, carrier sense multiple access. CD is nothing but collision detection to ensure that one device transmits at a time on a shared cable. The LLC sublayer, when we say LLC sublayer, which is logic link control, provides the interface to layer 3 and handles error detection and flow control. Whenever we talk about LLC, it is about handling error detection and flow control. Now, key functions of data link layer includes frame creation and recognition, putting boundaries around data so the receiving device knows where one frame ends and another frame begins. It performs error detection using techniques like CRC. What is CRC? CRC is cyclic redundancy check. We call it as cyclic redundancy check, which can detect if bits were corrupted during transmission. It provides flow control to prevent a fast sender from overwhelming a slow receiver, which we call it as flow control. Now, examples of data link layer technologies include Ethernet, which is what most wired networks use today, which is Wi-Fi or which is 802.11 for wireless networks, and PPP, which is nothing but point to point protocol, often used for connections to internet service providers. So the primary device operating at this layer are switches, which learn MAC addresses and forward frames only to the correct destination port, making networks much more efficient than the older hub based system. Now, layer 3, the network layer. So, the network layer is where we move from local communication to global communication. We are going from local to global. This layer provides end to end data delivery across multiple networks, which is exactly what we need for the internet. The network layer's primary responsibility is routing, determining the best path for data to travel from source to destination, even when they are on completely different network separated by multiple routers. This layer handles logical addressing using IP address, unlike the MAC address, which are tied to specific hardware. IP addresses are logical and can be assigned and reassigned as needed. IPv4 addresses look like 192.168.1.1. I'm just giving an example of an IPv4, while IPv6 is much longer. It would be like 0db8 or something like this. I'm just writing a random, IPv6. This is too long, whereas IPv4 is short and simple. Key functions include packet forwarding. Each router examines the destination IP addresses and decides where to send the packet next. Path selection uses routing algorithms to determine the best route through the network. The layer also handles traffic control to prevent network congestion. The main protocol at this layer is IP, which we call it as Internet Protocol, which defines how packets are structured and addressed. And ICMP is Internet Control Message Protocol. Internet Control Message Protocol. So handles error message and diagnostic information, like what you see when you see the ping command. And this ARP, which we call it as Address Resolution Protocol. translates IP address and MAC address. Routing protocols like we have, routing protocols like OSPF and BGP helps routers share information about network topology. The primary device operating at layer 3, okay, are routers, the primary devices, which connect different networks together, and layer 3 switches, which can perform routing functions at high speeds. When you send an email from New York to Tokyo, layer 3 protocol figure out how to get your data across multiple continents and through dozens of different networks. So this is all about layer 3, network layer. Now, layer 4, the transport layer, and this is where things get really interesting because this is where TCP and UDP operate. The main focus of our second half today. The transport layer provides reliable end to end. This, when I tell about transport layer, it provides end to end transfer between applications running on different devices. While layer 3 gets your data to right computer. Okay, layer 3, what it does is, I'll just type L3, there are, let's suppose there are so many computers. Okay, this is a sender, and this sender wants to send the message to this computer, which is receiver. One, two, three, four, and this is five. This sender wants to send it to fifth computer. The layer three's job is to identify the fifth computer and send the data to this fifth computer. That is the job of layer 3. While layer 4, the layer four's job is to, you know get it to the right application on that computer, to what application this data should be presented on. That is the work of layer 4. This layer ensures complete data delivery through several key functions. Segmentations and reassembly breaks large messages into, segmentation and reassembly, which breaks large messages into smaller pieces that can fit in network packets, then reassembles them at the destination. Flow control prevents a fast sender from overwhelming slow receiver. Error detection and recovery ensures that if data is lost or corrupted, it gets retransmitted. Port addressing uses port numbers to identify which application should receive the data. The two main protocols at this layer are TCP and UDP, and they take very different approach. TCP, which we call it as transmission control protocol, provides reliable connection oriented communication. It guarantees that data arrives complete, in order, and without error. It focuses on, and then we have UDP, which we call it as user datagram protocol, provides fast connectionless communication. It does not establish a connection, it is connectionless. This is connectionless communication. This is connection oriented communication. It establishes a connection, and it is reliable. This is fast connectionless. It focuses on speed. When I say fast, it focuses on speed and simplicity rather than reliability. It is not reliable. Think of TCP like sending a registered letter. You get a confirmation it was delivered. If something goes wrong, the postal service will try again. And think of it like this for TCP. Whereas UDP is like Shouting across a crowded room, it's fast and direct, but you can't be sure that message got through. Port numbers identify each application. You know, web servers typically use port 80 for HTTP and 443 for HTTPS. Email uses ports like 25 for SMTP, and we have 110 for POP3, and we have 143 for IMAP. This layer is crucial because it bridges gap between network infrastructure below and the application above. Let's move on to layer 5, the session layer. Now, the session layer manages communication session between applications. Think of it as the layer that handles the conversations, logistics between two applications that want to communicate. This layer establishes, maintains, and terminates connection between applications. When you start a video call, the session layer sets up the communication session. It maintains that session while you're talking, and it properly terminates the session when you hang up. Key function includes sessions establishment, negotiating the parameters for communication, like what protocols to use and how to handle errors. Session maintenance keeps the conversation going, handling things like keep alive message to ensure both sides are still connected. Session termination cle- you know cleanly closes the communication when it's no longer needed. The session layer also handles dialogue control, determining whether communication is full duplex, where both sides can talk at the same time, like a phone call, or half duplex, where only one side can talk at a time, like a walkie talkie. So, examples include NetBIOS sessions, which Windows computer use for file and printer sharing, RPC, which we call it as remote procedure call sessions that let programs call functions on remote computers, and SQL database session that maintains connection to database servers. In modern networking, many session layer functions are actually handled by applications themselves rather than by dedicated session layer protocols. But understanding this layer helps explain how applications maintain ongoing conversation across network. Layer 6, the presentation layer, is all about data transmission, data translation and transformation. This layer ensures that data sent by one system can be understood by another system even if they use different data format. The presentation layer handles data encryption and decryption. If protecting your information as it travels across networks. When you see that little lock icon in your web browser, SSL or TLS encryption is happening at this layer. For example, if I open some website, okay, let me just go for guruschools.com. So when I click on this, you see there's a HTTPS, right? When I open cyber secure analyzer, HTTPS, and if I open cyberspace techsolutions.com, you would see HTTPS. Okay, this layer also manages data compression and decompression. When you download a zip file or a stream video, compression algorithm reduces the amount of data that needs to be transmitted, making everything faster and more efficient. See, character encoding conversion is another key function. Different computer system might use ASCII, Unicode, or EBCDIC to represent text characters. The presentation layer ensures that a document created on one system displays correctly on another system. Data formatting handles things like converting between different image formats, audio formats, or document formats. When your computer displays a JPEG file, which is JPEG file, JPEG image, or plays an MP3 file, presentation layer protocol are involved. Example, you know, for examples, it could include SSL and TLS for encryption, which secures your online banking and shopping transactions. Compression formats like zip, JPEG for images, and MPEG for videos or video all operate at this layer. Character encoding standards like ASCII and Unicode ensures that text display correctly across different systems. In practice, many modern applications handle your own presentation functions rather than relying on separate presentation layer protocol. But the concept remains important for understanding how data gets transformed for transmission and display. Now layer 7, which is final layer, finally we reach to layer 7, the application layer, which is the layer closest to the end user. This is where network services are provided directly to user applications. The application layer provides the interface between network services and the applications that users actually interact with. When you open a web browser, send an email, open a web browser, send an email or transfer a file, you are using application layer protocols. Key functions include providing network processes access for applications, handling user authentication, right? It should be authenticated to verify who you are, enabling resource sharing like file and printer sharing, and providing remote file access so you can work with files stored on other computers. Common application protocols like HTTP and HTTPS for web browsing. If every time you visit a website, you are using these protocols. Email protocols like SMTP for sending mails, POP3 and IMAP for receiving mails, file transfer protocols like FTP for basic file transfer and SFTP for secure file transfer. And DNS, which we call it as domain name system, translates human readable domain names like google.com into IP addresses that computers can use. DHCP, dynamic host configuration protocol, automatically assigns IP addresses to device when they connect to a network. SSH provides secure remote access to another computer, while Telnet provides basic remote access. The application layer is where users actually see and interact with network services. It's the layer that makes networking useful for everyday tasks rather than just an interesting technical exercise. So, this completes a tour of OSI layers. Each layer builds on the services provided by the layers below it, creating a complete framework for network communication. Now let's see how all these layers work together when data actually flow through a network. Understanding this process is crucial for troubleshooting and system design. When you send data across a network, it goes through a process called encapsulation. As it moves down through the layers on the sending side, then it goes through decapsulation as it moves up through the layers on the receiving side. Okay, let's trace through a simple example. Imagine you are sending an email, your email application. Okay, your email application, that's layer 7, creates email messages, right? Email messages with headers like to, from, and the subjects. This is pure application data. Now layer 6, presentation layer, the data might be encrypted for security and compressed to reduce size. Layer 5, the session layer, adds information about maintaining the communication session with the email server. Now we reach layer 4, the transport layer, and this is where TCP comes in. TCP breaks your email into smaller segments. It's if it's large, adds sequence numbers so the receiving end can reassemble everything in the right order, and adds port numbers so the receiving computer knows this data is destinated for the email application. Layer 3, the network layer, adds IP addresses with source and destination IP addresses. This is what routers use to figure out how to get your email from from your computer to the email server, possibly across multiple networks and continents. Now, layer 2, the data link layer, adds frames headers with MAC address MAC addresses for the next hop in the journey plus error checking information. Finally, layer 1. The physical layer converts everything into electrical signals, light pulses, or radio waves that can travel across the physical network. At the receiving end, this process is reversed. So we were like top to bottom. Now this is reversed in the decapsulation, which is a reverse process. The physical layer converts signals back. The physical layer, see, while explaining, I'm explaining from here, application layer, this and this. Right now you see the layers are above here, layer 1, layer 2. Layer 1 is the physical, layer 3 is like this. It is reversed. So the arrow which I showed reverse here, which means if it could be, it is like this since the layer 1 is here. If the layer 1 was here, I would have shown this arrow would be right. Excuse me for that. Okay, the physical layer, which converts signals back to bits. The data link layer, again, checks for errors and removes frame headers. The network layer examines IP addresses and removes IP headers. The transport layer reassembles segments and removes TCP headers. The session layer, again, and the presentation layer and application layer does each processes with their respective headers until finally the email application receives the original message. This process happens millions of times per second across the internet, and understanding it helps you troubleshoot problems and design better systems. Now, benefits of OSI model. Before we move on to TCP and UDP, let's talk about why OSI model is so valuable, both for understanding networking and for practical work. From a technical standpoint, the OSI model standardizes network communication. Before standardization, every vendor did things their own way, and getting different systems to communicate was extremely difficult. The OSI model provides a common framework. It has a common framework that enables interoperability between different vendors and technologies. The model simplifies complex networking concepts by breaking them into manageable pieces. Instead of trying to understand everything about networking at once, you can focus on one layer at a time and understand how it relates to layers above and below it. For troubleshooting, the OSI model is invaluable. When you know when something goes wrong with network communication, you can systematically check each layer to isolate the problem. Is it a cable issue at layer 1, a switch problem at layer 2, a routing issue at layer 3? This systematic approach saves time and prevents the random troubleshooting that often makes problems worse. From an educational standpoint, the OSI model provides a structured learning approach. It gives students and professionals a logic progression for understanding networking concepts. It helps you understand the relationships between different protocols and technologies, and it provides a common vocabulary that networking professionals worldwide can use to communicate clearly. For practical application, the OSI model guides network designs and planning. When architecting new systems, you can think through the requirement at each layer. For security, you can implement protection at multiple layers, encryption at layer 6, firewall at layer 3, and physical security at layer 1. For protocol development, the model provides a framework for creating new networking technologies that will interoperate with existing systems. The OSI model also helps with performance optimization, but uh, you know, yeah, we could just say with it helps in performance optimization. By understanding what happens at each layer, you can identify the bottlenecks and optimize performance where it will have the most impact. Now let's shift our focus to TCP and UDP, two critical protocols that operate at layer 4 of the OSI model, the transport layer we discussed earlier. Both TCP and UDP serve the same basic purpose. They provide communication between applications running on different computers. However, they make fundamentally different approach to this task, and understanding when to use each one is crucial for anyone working with networks. So TCP stands for Transmission Control Protocol, and it's designed around the principle of reliability. TCP is connection oriented, which means it establishes a formal communication session before sending any data. It provides reliable delivery, guaranteeing that data arrives complete in the correct order and without errors. TCP includes extensive error checking and correction mechanism, and it provides flow control to prevent overwhelming the receiving system. Think of TCP like having a conversation with someone in person. You establish eye contact, you speak clearly, you wait for acknowledgements, and if the other person doesn't understand something, you repeat it. This ensures effective communication, but it takes time and effort. UDP. UDP stands for User Datagram Protocol, and it's designed around the principle of efficiency. UDP is connectionless, meaning it just sends data without establishing a formal session first. It provides fast transmission with minimal overhead. UDP doesn't include error recovery mechanism. It did if data get lost. UDP doesn't try to resend. There's no flow control, so UDP sends data as fast as the application provides it. UDP uses what we call best effort delivery. It tries to get your data there, but it doesn't make any guarantee. Think of UDP like shouting information across a crowded room. It's fast and direct, but you cannot be sure the message got through clearly, and you won't know if the other person missed part of what you said. The choice between TCP and UDP depends entirely on your application's requirements. Do you need guaranteed delivery, or is speed more important? Can your application handle missing or out of order data, or does everything need to arrive perfectly? Let's dive deeper into TCP and understand what makes it so reliable. TCP's reliability comes from several sophisticated mechanisms working together. First, TCP is connection oriented, which means it establishes a session before transmitting actual data. This happens through what's called the three-way handshake. The client sends a SYN packet saying I want to establish a connection with server. The server responds with a SYN ACK packet saying I acknowledge your request and I am ready to connect. Finally, the client sends an acknowledgement packet again saying, I acknowledge your response. Let's start communication. This is how the three-way handshake works. Only after this handshake does actual data transmission begin. TCP guarantees data delivery through a system of sequence numbers and acknowledgements. Every piece of data gets a sequence number, and the receiving system sends back acknowledgement confirming what it has received. If sender doesn't receive an acknowledgement within a certain time, it automatically resends the data. Flow control prevents a fast sender from overwhelming a slow receiver. TCP uses sliding window mechanism where the receiver tells the sender how much data it's ready to accept. If the receiver gets busy processing data, it can tell the sender to slow down or stop temporarily. Error detection happens through checksum that can detect if data was corrupted during transmission. If corrupted if corruption is detected, TCP automatically request retransmission of the affected data. So ordered delivery ensures that data arrives in the same sequence it was sent, even if network packets take different routes and arrive out of order. TCP uses sequence number to reassemble everything correctly. The TCP header contains all the information needed for these functions: source and destination port numbers to identify applications, sequence and acknowledgement numbers for reliable delivery, control flags for managing connections, window size for flow control, and checksum for error detection. This reliability comes at a cost. TCP has more overhead than UDP because of all these mechanisms. It's slower to establish connections because of the three-way handshake, and it uses more bandwidth because of all the acknowledgement and control messages. But for application where data integrity is crucial, like web browsing, email, or file transfer, this overhead is worth it to ensure reliable communication. Now let's examine UDP, which takes a completely different approach to data transmission. UDP is all about simplicity and speed. UDP is connectionless, meaning there's no session establishment process. An application can immediately start sending data without any preliminary handshaking. This makes UDP much faster to get started, but it also means there's no guaranteed communication path between sender and receiver. UDP provides fast transmission with minimal overhead. The UDP header is only 8 byte. 8 bytes compared to TCP's minimum of 20 bytes. This is for TCP and this is for UDP. This might not sound like much, but when you're sending millions of small packets, this difference adds up to significant bandwidth savings. UDP is unreliable in the technical sense. It sounds guarantee that data will arrive in order or arrive without corruption. This isn't necessarily a problem. It just means that applications using UDP need to handle these issues themselves if they matter for that particular use case. UDP has no flow control mechanism. It sends data as fast as the application provides us, regardless of whether the receiver is ready. Again, if flow control is needed, the application must implement it. The UDP header is beautifully simple. It contains just four fields, which is source, destination, length of the UDP datagram, UDP datagram, and checksum for basic error detection. That's it. No sequence numbers, no acknowledgements, no flow control information. This simply makes UDP perfect for applications where speed is more important than guaranteed delivery. Real time applications like online gaming can't wait for retransmissions. It's better to occasionally lose a packet than to delay the game for everyone. Video streaming application often use UDP because losing a frame occasionally is less noticeable than the delays that could come from retransmitting every lost packet. UDP is also ideal for simple request response protocols like DNS. When you look up a website address, your computer sends a UDP packet to DNS server asking for the IP address. The DNS server sends back a UDP packet with the answer. If the response gets lost, your computer just sends another request. This is much more efficient than establishing TCP connection for such a simple transaction. Now, TCP versus UDP comparison. Let's directly compare TCP and UDP across all the key characteristics that matters for network applications. Starting with connection management. TCP is connection oriented, requiring three-way handshake we discussed before any data transfer. This ensures both sides are ready to communicate but adds latencies. UDP is connectionless. You can start sending data immediately, which is much faster but provides no guarantee that the receiver is ready. Now, for reliability, TCP provides guaranteed delivery. through acknowledgements and retransmission. If data gets lost, TCP will detect this and resend it automatically. UDP uses best effort delivery. It tries to get data there but doesn't guarantee success. If reliability is needed with UDP, the application must implement it. Speed difference are significant. TCP is slower due to connection overheads, acknowledgements, and potential retransmissions. Every TCP segment needs to be acknowledged, which means more traffic and delays. UDP is much faster because it has minimal overhead and no waiting for acknowledgements. Error checking varies between the protocols. TCP has extensive error detection and correction. It detects lost, duplicate, or corrupted data and fixes these problems automatically. UDP has only checksum error detection. It can detect if data was corrupted but won't attempt to fix the problem. Okay, excuse me. Flow control is another major difference. Yes, TCP implements sophisticated flow control to prevent overwhelming the receiver. The receiver can tell the sender to slow down or stop if necessary. UDP has no flow control. It sends data as fast as the application provides it, regardless of receiver's capacity. For data ordering, TCP guarantees that data arrives in the same sequence it was sent, even if individual packets take different network paths. UDP provides no ordering guarantees. Packets might arrive out of sequence, and the application must handle this if order matters. The header size impacts efficiency. TCP headers are at least 20 bytes and can be much larger with options. UDP headers are always exactly 8 bits. For small messages, this difference is proportionally significant. The choice, the choice of use case reflects these characteristics. TCP is perfect for web browsing where you need complete web pages, email where messages must arrive intact, and file transfers where every bit matters. UDP excels at online gaming where real time response matters more than perfect data. Video streamings where occasional lost frames are acceptable, and DNS lookups where simple request response patterns work best. Let's look at specific applications that rely on TCP and understand why TCP is the right choice for these use cases. So, TCP is essential for web browsing using HTTP and HTTPS. When you visit a website, your browser needs to download HTML files, CSS style sheets, JavaScript code, images, and other resources. Every piece must arrive complete and in the correct format, or the web page won't display properly. TCP's reliability ensures that you get the complete web page, not a corrupted version missing critical elements. So email systems depend heavily on TCP. SMTP uses TCP port 25 for sending mail between servers. POP3 uses TCP for 110 for downloading mail to your computer. IMAP uses port 143 for accessing mail stored on servers. Email messages must arrive exactly as sent. You can't afford to lose parts of important business communication or have words corrupted during transmission. File transfer applications are perfect examples of why TCP matters. TCP uses TCP port 21 for control and port 20 for data transfer. SFTP uses TCP port 22 for secure file transfer. When you are transferring a document, software update, or any other file, every single bit must arrive correctly. A single corrupted bit could make a document unreadable or a program unusable. Remote access protocols rely on TCP's reliabilities. SSH uses TCP port 22 for secure remote access to another computer. When you're typing commands on a remote server, every keystroke matters, and the responses must arrive complete and in order. Even older protocols like Telnet use TCP because interactive sessions require reliability. Order communication. So the common thread among all these applications is that data integrity is more important than raw speed. These applications can tolerate the additional latencies that comes with TCP's reliability mechanism because getting correct, complete data is essential for proper operations. So TCP's connection oriented nature also provides security benefits. The three-way handshake makes it harder for attackers to inject malicious packets into ongoing communications. And the connection state helps firewalls makes better decisions about which traffic to allow. Now, UDP applications. Let's examine applications that choose UDP and understand why speed and efficiency matters more than guaranteed delivery for these use cases. So, online gaming is perhaps the best example of why UDP is sometimes the right choice. In a fast paced multiplayer game, players need to see movements and actions from other players as quickly as possible. If a packet containing a player's positions gets lost, it's better to skip that update and wait for the next one rather than delay the entire game while TCP retransmits the lost packets. Games typically send positions updates many times per second, so losing one occasionally isn't noticeable, but delays would ruin the game experience. Video and audio streaming application often use UDP for similar reasons. When you are watching a live stream or a video call, it's better to occasionally lose a frame than to pause the entire stream while waiting for retransmission. Your brain naturally interpolates over small gaps in audio or video, but it definitely notices delays for stuttering caused by waiting for perfect data delivery. DNS, the domain name system, is a perfect example of UDP's efficiency for simple transactions. When your computer needs to look up the IP addresses for a website, it sends a small UDP packet to a DNS server. The server responds with another small UDP packet containing the answer. The entire transaction typically takes just a few milliseconds. If the response gets lost, your computer simply sends another request. Establishing a TCP connection for such a simple exchange, would add unnecessary overhead and delay. Now, DHCP, Dynamic Host Configuration Protocol, uses UDP for automatically assigning IP addresses to devices joining a network. When your laptop connects to a Wi Fi network, it broadcasts a DHCP request using UDP. DHCP servers respond with UDP packets containing IP addresses assignments. This needs to be fast and efficient, especially in environments where many devices are connecting and disconnecting frequently. Now, network management protocols like SNMP, simple which we call it as simple network management protocol, often use UDP for collecting statistics from network devices. These applications send frequent small queries to many devices and need the efficiency that UDP provides. The key insight is that these applications either handle reliability at the application level when needed, or they are designed they're designed so that occasional data loss isn't a problem. They prioritize speed and efficiency over guaranteed delivery. Now, TCP IP model versus OSI model. Now let's explore how the theoretical OSI model relates to the practical TCP/IP model that's actually implemented in real networks. This comparison helps bridge the gap between conceptual understanding and practical applications. The TCP/IP model, also called the Internet Protocol Suite, is what actually runs the internet. It was developed in 1970s by DARPA for the project, for ARPANET project, which eventually became the internet. While the OSI model has 7 layers, the TCP IP model has 4 layers. And there's an important reason for this difference. The TCP/IP model's application layer combines the functions of the OSI model's application, presentation, and session layer. In practice, most modern applications handle presentation and session functions internally rather than relying on separate protocols for these functions. For example, web browsers handle HTML formatting, image decoding, and session management as part of the application itself. The transport layer in both models is essentially identical. This is where TCP and UDP operate, providing end to end communication between applications. The functions and protocols are the same whether you are thinking in terms of OSI model or the TCP IP model. The internet layer in the TCP IP model corresponds to the network layer in the OSI model. This is where IP Internet Protocol operates, handling routing and logical addressing. The functions are identical, it's just a naming difference. The network access layer in the TCP IP model combines the OSI model's data link layer and the physical layers. In practical implementation, these are often tightly integrated. Ethernet, for example, defines both physical signaling and frame formatting as a single standard. The reason for these difference is that the OSI model was designed as a comprehensive theoretical framework, while the TCP/IP model evolved from practical implementations. The OSI model provides excellent conceptual understanding, but the TCP/IP model reflects how networking actually works in the real world. Both models are valuable. The OSI model is better for education and troubleshooting because its 7 layer provides more granular analysis of network functions. The TCP/IP model is better for understanding actual network implementations because it matches how protocols are really organized and deployed. Let's look at exactly how the layers map between these two models and what protocols operate at each level. The TCP/IP application layer encompasses all user facing network services. This includes HTTP and HTTPS for web browsing, which handles not just data transfer but also formatting and session management. FTP provides File transfer capabilities. SMTP, POP3, and IMAP handle various aspects of email. DNS translates human readable domain names into machine readable IP addresses. All of these protocols include functionality that would be distributed across multiple layers in the OSI model. Now, the transport layer is identical in both models. TCP provides reliable connection oriented communication for applications that need guaranteed delivery. UDP provides fast connectionless communication for applications that prioritize speed over reliability. Port numbers at this layer identify specific application running on each computer. The internet layer maps directly to the OSI network layer. IP Internet Protocol is the primary protocol here, handling logical addressing and routing between networks. ICMP, which is Internet Control Message Protocol, provides error reporting and diagnostic functions like what you see when when you see ping or trace route commands. Then ARP, which is Address Resolution Protocol, translate between IP address and physical MAC address. The network access layer combines OSI's data link and physical layer because they are typically implemented together in real world technologies. Ethernet defines both the physical signaling and the frame format. Wi Fi standards include both radio specification and data formatting. These technologies handle getting data reliable from one network node to the next adjacent node. Understanding this mapping helps you apply OSI concepts to real networking situations. When troubleshooting, you might think in terms of OSI layers for systematic analysis, but when configuring actual equipment, you will work with TCP/IP protocols and settings. Now, let's trace through a real world example to see how everything we have discussed work together. Okay, imagine you're sitting at your computer and you're typing www.google.com. Okay, into your web browser and press enter. Let's follow the request through the network stack. First, your browser, that's the application layer, creates a HTTP request, HTTP GET request from Google's homepage. The browser doesn't know Google's IP address, so it first needs to perform a DNS lookup. It sends a UDP packet to your configured DNS server asking what's the IP address for www.google.com. The DNS server responds with something like the IP address, which would be like 172.217.14.196, something like this. A IP address, a clean, nice IP of the Google. This DNS transaction uses UDP because it's simple request response that needs to be fast. Now your browser can make the actual HTTP request. Since web pages must load completely and correctly, this uses TCP. Initiates TCP three-way handshake with Google's web server on port 443. Why port 443? Because it is HTTPS. For your computer, your computer sends SYN, Google server sends SYN acknowledge. Okay, let's suppose, this is Google server. Okay, let's suppose this is a Google server. Your computer is sending SYN. Let me delete things. Okay, this is Google's server. Your computer is sending SYN. Okay, and it gets back a response. What response it gets? It sends sin acknowledge. And then your computer sends an acknowledgement to Google server. Now a three-way handshake is done. Connection is established. Now you have a reliable TCP connection established. Okay. Your browser sends a HTTP GET request over this TCP connection, and the transport layer TCP breaks this request into segments if necessary, adds sequence number, and includes port numbers. Your browser might use port 52847, while Google's server uses 443 as the destination. The network layer adds IP headers with your computer's IP address has the source and destination's IP address has the destination. Your local router examines this destination and determines that Google isn't your local network, so it forwards the packet towards your internet service provider. The packet travels through multiple routers across the internet. Each router examines the IP headers and consults its routing table and forwards the packet towards the destination. This might involve hops through your ISP, major internet backbone providers, and eventually to Google's network infrastructure. At the data link layer, okay, each hop involves removing the old Ethernet frame header and adding a new one appropriate for the next network segment. The MAC address change at each hop, but the IP addresses remains the same throughout the journey. When the packet reaches when the packet reaches the Google servers, the entire process reverses. Google servers processes your HTTP request, generates an HTML response, and sends it back through the same layered process. Because you are using TCP, Google servers can send the web page in the multiple segments, and your browser will receive acknowledgments and reassemble everything in the correct order. This entire process from typing a URL to seeing the web page typically takes a few hundred milliseconds, but it involves dozens of network devices and thousands of protocols operations working seamlessly together. Now, let's see how understanding these models helps with practical troubleshooting. When someone says the internet is down, that's not very specific. But the OSI model gives us a systematic approach to diagnose the real problem. So we start at a bottom, with layer one, the physical layer, right? Excuse me. Check the obvious things first. Are all cables plugged in securely? Are there any visible damage to cables? Are all network devices powered on? Do you see link lights on network interface? These might seem basic, but physical problem cause a surprising number of network issues. Now moving to layer 2, the data link layer, we check local network connectivity. Can you communicate with other devices on the same network segment? Are switch port lights indicating activity? If you're using wireless, are you connected to the right network with a good signal strength? You might use tools that show MAC address tables to verify that switches are learning device location correctly. At layer 3, the network layer, we test IP connectivity. The ping connect, command is perfect for this. It uses ICMP to test whether you can reach specific IP address. Try pinging your default gateway first, then try pinging a well-known public address like 8.8.8.8, which is Google's public DNS server. The traceroute command shows you the path your packet take through the network, which can reveal where connectivity breaks down. At layer 4, the transport layer is where we test specific services. You might use telnet to test whether you can connect to specific TCP ports. For example, telnet google.com 80, like this. For example, google.com 80 port, right? I can do a telnet and test whether you can establish a TCP connection. The netstat command shows you what TCP and UDP connections are currently active on your computer. For upper layers, we test specific applications. Can you resolve DNS names? Can you browse the web? Can you send email? Each application test helps narrow down whether the problem is with basic connectivity or with specific services. The beauty of this approach is that it's systematic. Instead of randomly trying different things, you work your way up the track. If layer 1 tests fail, there's no point testing layer 3. If layer 3 tests work better than layer 7 applications fail, you know the problem is somewhere in the upper layer. Tools that help with analysis include Wireshark for capturing and analyzing the packets at all layers, Ping and traceroute for layer 3 testing, netstat for viewing connection states, and NSLOOKUP for you know uh, NSLOOKUP or dig for testing DNS resolution. This systematic approach saves time and prevents the frustration of chasing symptoms rather than root causes. Okay, as we wrap up, let me share some best practices and key insights that will help you apply this knowledge effectively. For protocol selections, always start by understanding your application's requirements. If data integrity is critical, like financial transactions, email, or file transfers, choose TCP despite its overhead. The reliability is worth the performance cost. If real time performance matters more than perfect delivery, like gaming, live streaming, or simple queries, UDP's speed advantages must make it the better choice. Don't automatically assume TCP is always better. Understand the trade offs. For security considerations, remember that security works best when implemented at multiple layers. Use encryptions at the presentation layer with protocols like SSL and TLS. Implement firewalls at network layer to control traffic based on IP addresses and ports. Use secure transport protocols when available, HTTPS instead of HTTP, SFTP instead of FTP, SSH instead of Telnet. Monitor network traffic at multiple layers to detect anomalies and potential attacks. Performance optimization should be based on understanding what happens at each layer. Network latency might be a physical layer issue with long cable runs, a network layer issue with inefficient routing, or a transport layer issue with TCP's flow control. Bandwidth limitation might be physical constraint or might be caused by protocol overhead. Understanding the layers helps you optimize where it will have the most impact. So for troubleshooting, always work systematically through the layers rather than jumping to conclusions. Document your findings at each layer. This helps you avoid repeating tests and helps others understand your diagnostic process. Use appropriate tools for each layer and understand what each tool actually tests. Remember that in real networks, the TCP/IP model is what's actually implemented, but the OSI model provides the best framework for understanding and troubleshooting. Use OSI concepts for analysis and TCP/IP knowledge for implementation. One crucial insight is that understanding these models help you make better technology decisions. When evaluating new networking technologies, you can analyze how they fit into this framework and predict how they'll interact with existing systems. Finally, keep in mind that networking technologies continues to evolve, but these fundamental concepts remain constant. New protocols and technologies still fit within these layered models, so the time you invest in understanding these concepts will pay dividends throughout your career. The goal isn't to memorize every detail, but to understand the principles so you can think systematically about networking problems and solutions. So, just a summary, the recap what we had. Okay, the OSI model, 7 layers, standardized network communication, enables troubleshooting and design. Each layer has specific responsibilities. Then we saw about TCP UDP protocols, the 4 layers. Then TCP and UDP difference between these two, choosing the best application based on the use case. Then understanding the key benefits, understanding troubleshooting, design, and career. Now, similar to all other labs, we have a lab for this as well. I have designed a lab specifically for this for this use case. So here is the link for the lab. So where you can go through interactive lab, it's a good lab. You can go through each of these, learn about it. Once you see the functions and protocols, answer the question which layer handles IP addresses. Okay, you can say network. Is it correct? Yes, correct, 10 point. Then complete exercise 1. You have exercise 2. You can just drag and drop all the layers where you think it fits good. I'm just, when I just drag and drop, you see not quite doesn't match. Wherever it matches, you can just drag and drop. It says not quite matches. Then again, Ethernet where it sits, SLS, TLS where it is not sitting there. Okay, then DNS where it comes, not quite. Okay, here. Physical layer, UDP sits here. It completes. Complete exercise 2. I'm just showing you the example. You can go through it, go through the lab, send email, it simulates it this way, and you can stream the video of UDP, and you can answer this and go to the next session. You can give the command, and you can work around this. Okay, enter the command, try completing the exercise. We have 5 exercises. Try to do with this. So I hope you had a good time. It was a very lengthy session. Thank you for your attention. Any doubts, anything, you can comment and you can send me a query. I'll be happy to answer. And so we'll see what would be our next session. Until then, happy learning. Thank you.